We've all experienced the dread of sitting in a patient's chair, endlessly waiting for our blood to be drawn. Aside from the typical fear of needles, blood tests, despite their precision, only provide a single snapshot into our physiological state. This approach is often inadequate for life-threatening conditions such as sepsis, where monitoring fluctuations in biomarker levels over a period of time is critical for early detection and treatment. My name is Shravya Pilla, and this is a wearable, high-sensitivity biotransistor for the detection of lactate in sweat. Sweat is a constantly produced, non-invasive body fluid rich in diverse biomarkers, making it especially useful for continuous detection. Because it can be collected easily from the skin without discomfort, sweat offers a convenient way to track real-time changes in physiological processes through wearable sensors. Among the analytes in sweat, lactate is particularly significant due to its relation to oxygen levels, metabolic health, and even stress and fatigue. But the problem is, lactate levels change rapidly. Therefore, traditional serum tests, while accurate, are invasive and provide only momentary snapshots rather than real-time trends. This gap highlights the need for wearable, non-invasive sensor capable of tracking lactate continuously and capturing these rapid physiological changes as they occur. Unfortunately, most existing lactate sensors are limited. They can only detect low concentration ranges, rely on costly materials like gold or platinum, or respond too slowly to be practical. To address this, I developed an organic electrochemical transistor, OECT. This device detects lactate by converting it into measurable ions through enzymatic reactions involving lactate oxidase and Prussian blue. The transistor consists of 4 key components: a gate electrode, a channel, a source pad, and drain pad, connected by conductive traces that enable controlled current flow. The OECT operates by sensing electrochemical reactions at the gate electrode, which modulate the conductivity of the P.PSS channel. This change produced an amplified electrical signal, allowing the device to accurately reflect variations in lactate concentration. My project focused on 4 key experiments: determining the most sensitive OECT design, establishing a baseline response using phosphate buffer, testing the specificity to lactate, and measuring the sensor's response time. Phase 1 focused on sensitivity testing to identify the most effective sensor design. Using highly capacitive electrode materials resulted in an exceptionally high sensitivity, confirming that this configuration was suitable for further experimentation. Phase 2 established the sensor specificity by showing that plain sweat did not deplete or activate the device. The sensor produced a response only when lactate was present, demonstrating a stable and selective baseline. The final phase evaluated response speed. When exposed to the highest physiological reported lactate concentration in sweat, the sensor produced a clear signal within just 2 minutes, markedly faster than many existing sweat detection technologies. Overall, the sensor met all 3 design goals. It achieved a wide range of detection, high sensitivity, and fast response, all using inexpensive materials that total around $6 per device. The future applications of this project open up a variety of doors in healthcare. Since most compounds found in sweat can be converted to hydrogen peroxide, the created sensor can be adapted to diagnose numerous conditions. With more iterations and improvements, this sensor can be worn as a wearable technology. Through a mobile app, users could receive personalized diagnostics in the real time, blending the accessibility of fitness trackers with the precision of high-end medical tools. With artificial intelligence and machine learning revolutionizing data analysis, this innovation has the potential to redefine predictive medicine and make personalized healthcare closer to a reality, one drop of sweat at a time.